All right, so in this video, we continue our mechanics of material sequence, and we're doing an example problem for the average normal stress and average shear stress of an axially loaded bar. I've got here in this bar 85 pounds being applied through the center of the cross section, and the cross section has dimensions of 1 inch by 3 inches. And what I want to do is find the average normal stress sigma, which is we're going to apply that equation, normal force divided by the internal normal force divided by the cross-sectional area that normal force is acting on, and then the average shear stress, which is just V over A as well. Okay, and then what we want to do is find this normal stress and shear stress along a 15-degree slice, okay, 15-degree slice or plane of the structural member, and see what those are, okay? And so, as you can imagine, one of the first things you need to do is draw a free body diagram. When you make this cut here, when you make this cut on this plane, you can look at the left side of your diagram or the right. You should get the same result either way. I'm going to look at the right side because, for me, I'm not a great artist or anything, and so it's easier for me to just draw the right side and see that in 3D, because then I get to see the whole surface, whereas if I look to the left side, that surface looks a little hidden. But whatever, okay? And the other thing that's really important is that when you make that cut, you have to draw, or you have to write out what the internal, the internal loads are on the inside of that, once inside of the member after you cut it. And so here, in this case here, I have a normal force. Bam. I have a normal force on the inside, which I will draw perpendicular. Now, I'll assume that it's positive, causing tension on this face, on this blue area, or the cut, the plane of the cut. And then I'm going to have a shear force, and I'm also going to assume that it's just moving to the right here, and the shear force here, V, is going to the right, upwards, if you will, in the upward sense. Okay, I could draw a moment here as well. I could draw a moment like this here, but because everything is concentrically loaded, this P acts through the center right here. This moment, there is going to be no moment induced on this. Okay, which also means that I have no moment equation that I can apply. Trying to erase this, got to get rid of that. So forget this moment, there's no need for it. Okay, so that moment would be 0 if I applied an equilibrium equation. And so now I have this, this internal loading, and I only have 2 internal loads, the normal force and the shear, which I have to calculate using equilibrium equations. All right, so equilib equations to calculate internal loads, something you've been doing since, who knows, maybe physics. Okay, but here, you have a couple choices here. A lot of times people might just do some, X as positive horizontal straight across and vertical as positive Y, and some forces in the vertical and the horizontal. And what that's going to do, if you just go straight across for the horizontal, what you're going to have is you're going to have 2 equations, and they're going to be coupled equations, meaning that I'm going to have, if I do some of the forces in the horizontal, I'm going to have N and V appear in that horizontal equation. So here, let's see what that would look like. I'd have this. So I'd have here, if I just did, say some of the forces in the X equal to 0, and I said horizontal here, like this, I might have V cosine of 15 degrees minus N sine of 15 degrees plus 85 pounds equals 0. And so essentially what you're going to see is some of the forces in the Y equal to 0, and I would have V sine of 15 degrees. If I say this is positive, V sine of 15 degrees plus N cosine of 15 degrees equals 0. And I have 2 equations, 2 unknowns, I can solve it, right? The other thing you could do, though, is, this is one option where you have just straight across, horizontal and vertical. Another option is to say, here, I'm going to call this plus X, and I'm going to call this parallel to my normal force plus Y right here. And if I do that, when I do sum of the forces in the X equal to 0, and X will be this way positive right here. So this is, anyway, right here. I have V, and then I have, again, let's here break this up. We're going to have this here. That'll be X. So I will have here this P, I'll have a PX component and a PY component right here. I'm just breaking up a vector, okay, into an X and Y components right here. So here I'd have V my plus P cosine of 15 degrees. This is my px, okay, equals to 0. And then I have, if I do sum of the forces in the y equal to 0, and this would be the positive y there, I'd have n minus p sine of 15 degrees equals 0. And this, as you probably gathered, is py right there. And so here, if you look at this right here, if I stick with the straight horizontal and vertical as I'm used to, or you might be used to right here, I get two coupled equations, right? So I have to solve two equations to unknowns. Whereas here, if I just change my axes, my x and y to coincide with the shear and the normal force, then I have two equations, two unknowns. I don't have to worry, but it's real simple, right? And I get right away that this, this P is 85 pounds, just in case you didn't know that. This number should be 85 pounds, and that is 85 pounds. So when I solve this out, I would get that V is equal to negative 82.10 pounds. And that negative just means it's 82.10 pounds, not in the direction that I drew it. It actually goes this way, is my direction. And my normal force is positive 22.0 pounds, which indicates that my normal force is 22.0 pounds in the direction that I drew it, this way right here. Okay, so those are my internal shear and normal forces acting on this cut at 15 degrees in this blue zone. Now the next thing that we need to do to just is apply these equations here, apply these constitutive equations for shear stress and normal stress. But what we need is the area that we're acting on. And so probably the trick in this problem, or the challenging aspect of it, is to accurately determine. So we want to apply equations. Here is our next step here. But we need some geometric properties, in particular this blue zone, which I'm going to call A star. Okay, and if you look here, if you remember, this width right here is 1 inch, and the original area, which I will look at this, the original cross-sectional area, this area is length times the width, which is 3 inches, times 1 inch, which was 3 inches squared. Okay, and here in the blue area, in my 15-degree cut, my width does not change. I think you will agree with me on that. This width right here is still 1 inch, but I have a new length right here, and that would be L star. Okay, and that makes my area, my new area, equal to uh, L star times W. Okay, so what is L star? L star, if I have here, if I know that this vertical height is 3 inches and my angle is 15 degrees, aha, I just know that based on sine of 15 degrees is equal to the opposite, 3 inches over the adjacent, which is over the hypotenuse, which is L star. Okay, or let me, oh no, don't crash on me. Okay, right here, let's just make this, let's say the original length over L star right here. So that makes L star equal to L over sine of 15 degrees. And if I plug that into here, that tells me A star is just length times width divided by sine of 15 degrees, which was really just 3 inches squared divided by the sine of 15 degrees. And that is, this A star, if I run through some calculations, is 11.59 inches squared. And just to finish it all out, to calculate at last, applying these relationships, so the normal stress sigma n divided by A star is equal to what, 22 pounds divided by 11.59 inches squared, which is 1.90 psi, or pounds per square inch, and tau, which is V over A star, and that was 82.10 pounds divided by 11.59 inches squared is 7.08 psi, and that is it. Oh, I apologize if I was a little wordy at the beginning. Anyway, hopefully you enjoyed it, and maybe I'll do something a little bit more difficult next time. All right, enjoy.